Hello. Find the absolute extrema of the following functions on the given interval. So we'll do one example at a time. Step 1. Find the critical numbers. How do we find the critical numbers of the function? Very good. What is the first derivative? 3x squared plus 6x plus 3. So we have to see where it equals 0. See where it does not exist. What is 3x squared plus 6x plus 3? What do all those terms have in common? 3, pull out a 3. Now you don't have to pull out a 3. Since this is an equation, what else can you do with that 3? Divide each side by 3. So the 3 doesn't matter. So how does x squared plus 2x plus 1 factor? X plus 1 squared? So again, if you want the 3 there, that's fine. Or you can divide both sides by 3. You technically have a product that equals 0. When does 3 equal 0? Never. When does x plus 1 equal 0? So again, that part there was when the derivative equals 0. And how about the derivative does not exist? Not going to happen. Why? It's a polynomial. No fractions, no radicals, no logs. Yay. Step 2. 2 and 3 you can make into one step. And this is where your chart comes in. So the x values, notice our a here is what? What's the left-hand side of that interval? -3. And notice -1 is between -3 and +4, so we'll include it. And then the right-hand side of the interval is 4. So if, for instance, we got 5 as a critical number, well, 5's not in that interval, so you won't include it. Okay? So it has to be between -3 and 4. You're going to stick in these 3 numbers into your original function. So if you want to make a table in your calculator, go right ahead. Put a -3 into the original function, what do you get? Huh? Like the show? -1, 20, and 4. You got 16, not 20? You got 16? All right. And everyone learned their lesson from last time where someone gave me a false answer and I went with it, right? 16. And what'd you get for 4? 109. They're all wrong? All right. Well, good thing we're not recording this for prosperity then. Absolute man. All right, hold on. Now I'm going to glare at each and every one of you. I'm going out of order here because I want to do the third one second. So if you would, find the first derivative, see where it's 0, see where it does not exist. I'll do the does not exist part. It never not exists. You're welcome. Go from there. And we're going to use Mayan numerals to number the steps there. You're welcome there. There you go. X squared minus 6x plus 8. Let's see where it equals 0. How does x squared minus 6x plus 8 factor? Tell me about x. And how about where it does not exist? Even though I already said this one. Does not exist. Steps 2 and 3 are your chart. 2 and 3. Look, you guys are learning a whole new number system. And by whole new, I mean thousands of years old, so it's really not new. Okay, what numbers do I put in the chart? -4, 2, and 3. Why don't we put +4? Yep, it's bigger than 3. So even though 4 was a critical number, it's not in our restriction from -4 to +3. Because 2 was a critical number. Put in -4, +2, and +3 into your calculator. So what do you get at negative 4? All right, so what does negative 4 give you? Negative 91. Yay. I think we're going to go back to that strapping on the bomb thing. 0.33, yes. How about 2? 667? So that's really 16 2/3. And this is really negative 91 1/3. Honestly, I would prefer a fraction. They're not that bad for this problem. And 3? 16 even? Awesome. Okay. Absolute max. Absolute min. We're going to go back to the second example to do that third. It's insane. Because now notice it's no longer an open interval. Excuse me, it's no longer a closed interval, it's an open interval. We do the exact same stuff, except 3. We don't make a chart. Instead, since it's open, we use limits. Okay? So these happen to be approaching infinities. You would do the same thing if it were approaching a number. So you can't plug in infinity. You would have to find the limit as x approaches infinity. So we'll do it again. Look at this different numbering system. So what is the first derivative? So just like we had before, 3 times the quantity x plus 1 squared. And as we had before, this equals 0 when x equals negative 1. And previously we found g of negative 1, negative 16. So that's our only critical number, is that negative 1. And its corresponding y value is negative 16. So off to the side, what we do is we find the limit as x approaches infinity of the function. And then we'll also do as x approaches negative infinity of the function. What only matters here is the first term. So even though that's a huge polynomial, all that matters is the x cubed. So as x gets more and more positive, what happens to x cubed? Gets bigger in what direction? Positively or negatively? Right. So this is going to shoot off to positive infinity. Since that goes bigger and bigger in the positive direction forever, is there any absolute max? No. So for x approaching negative infinity, again, looking only at the first term, well, when you cube a negative number, it stays negative. So this is going to get closer and closer to negative infinity. So is there any absolute min? No. So is negative 1 comma negative 16 anything? No. It's neither a max nor a min, because there can't be any maxes or mins. So you would say no absolute extrema. Now if, for instance, instead of a cubic, if it was an even power, like an x to the 4th, that means they would both shoot off to the same direction, like for instance, positive infinity. So if the tails are going at positive infinity, then what would this mean? This would be an absolute minimum. Okay. So even though we did this as our first example, where on a closed interval it had an absolute max and an absolute min, that's guaranteed from the extreme value theorem. However, when you're on an open interval, you have no guarantees.